Consider two vectors v and w in the Euclidean plane. We can add them together and think of v plus w as placing the tail of v at the tip of w. We call this shift of v a translation by w. It's easy to get v plus w with pencil and paper. You just add the coordinates of v and w. But here's an issue. Translation by a vector like w is not a linear transformation. This means that there is no 2 by 2 matrix we could multiply v by to obtain v plus w. To see this impossibility, observe what happens when v is the zero vector. A matrix times a zero vector is just the zero vector, but w, the vector we're shifting v by, is not the zero vector. This matters because computers, especially GPUs, are optimized for matrix operations. If we want fast, efficient graphics and geometry computations, then we need transformations to be linear. The fix? Use homogeneous coordinates. It's an idea from projective geometry. This lets us embed the Euclidean plane R2 into the real projective plane RP2. We extend our vectors into 3D by appending a third coordinate z. In projective geometry, vectors with z-coordinate 0 are called points at infinity. These points are useful for manipulating perspective in a scene, but not for implementing translation, so we won't talk more about them in this video. The vectors with z-coordinate 1 in the real projective plane are what we'll use to correspond to our vectors in the Euclidean plane. The goal is to find a matrix that we can multiply by v and get v plus w with z-coordinate 1. These homogeneous coordinates provide us with extra freedom for constructing a matrix to do the translation job in the plane defined by the equation z equals 1. Consider this matrix that looks like the 3 by 3 identity matrix, but whose last column begins with the coordinates of w. We're doing the first part of this matrix multiplication slowly in case it's been a minute for you, but let's now kick it into warp speed. The result of this matrix multiplication is exactly what we wanted. It's v translated to w in the plane z equals 1. There's some deeper mathematics going on here too. We've realized translation of a vector as the action of a matrix Lie group that pretty soon we'll call G. And we've actually defined an isomorphism between the Lie group of 2D vectors that we can add component-wise and the group of matrices G that we can multiply together. The matrix Lie groups are especially useful in theoretical physics and chemistry because they provide a rigorous mathematical framework to describe conservation laws. This video is a short one, trying to get back into the habit of posting. I hope you enjoyed the math that we talked about here.